Hello everyone, I am Ved Datar, faculty member in the Department of Mathematics at the Indian Institute of Science. So, welcome to the first lecture of the NPTEL course on Riemannian geometry. So, since this is the first lecture, I thought we will start with something very basic. One of the main sort of objects of interest in this course is going to be to understand curvature of Riemannian manifolds. So, I thought in the first couple of lectures let me just start with essentially multivariable calculus and a little bit about curvature of curves and surfaces in the Euclidean space. So, today to begin I wanted to do something, I wanted to really go back to one of possibly the first theorem that we ever learn in high school. I remember when I was in 8th standard, I think I had first come across this theorem, namely the sum angle property of triangles, right. So, I think that is a good starting point, and from there I'll explain a little bit in the next couple of lectures how to try to extend that to more general spaces, and I think that would be a good starting point for us to begin this course with. Okay, so as I said, I mean today I'll first talk about the sum angle property of triangles. Alright, so let us begin with sort of the main theorem that we learn about in high school. So, consider a triangle let us call it A1, A2, A3 in the Euclidean plane, which I will denote by R2, and let us say with interior angles alpha 1. So, the angle at A1 is alpha 1, the angle at A2 is alpha 2, and the angle at A3 is alpha 3. So, let me maybe draw a picture. So, this is A1, A2, A3, this is alpha 1, alpha 2, alpha 3. Then the sum of angles of the triangle is 180 degrees, or in terms of radians it is pi radians, right. Okay. So, actually it is possibly more useful sometimes to state this theorem in terms of the external angles. So, let the external angles be epsilon 1, sorry this should be the epsilon 2 and epsilon 3, then this statement is equivalent to the statement that the summation of the external angles is exactly 2 pi. Okay. So, now I want to consider the following two generalizations. So, firstly I want to try to see if one can generalize this to curved triangles. Okay, so, of course triangle by definition is made up of 3 vertices and the vertices are connected by straight lines, but instead one could try to connect the vertices by some curved smooth path, let us say, and try to understand if there is an analog of the sum angle property for such triangles. And the second way in which I would like to generalize this is to try to understand this property for triangles on curved surfaces. So key assumption in this theorem is that our triangle lies on the Euclidean plane, right. On the other hand, one can, for instance, think of triangles on spheres, right. Of course, an important question to first address is what do you actually mean by a triangle on the sphere, right. So I'll get to that later in this lecture, but presumably one could have one could make sense of triangles on such curved surfaces and then ask if the sum angle property is correct, or if there is an analog of the sum angle property, right. So all right, so let me first start with curved triangles. Curved triangles in the plane, so in R2. Okay. So let me maybe draw two pictures. Oh, sorry. So let me draw a sort of fat triangle and let me draw a thin triangle. Okay. So let's instead of again looking at the sort of interior angles, let's look at the exterior angles. So the exterior angle is the angle made between the tangent vectors to these curves at these 2 points, and let's call the thin triangle as A1 prime, A2 prime and A3 prime. Okay, so let's mark out the external angles. Sorry. So for the fat triangle, it's kind of clear that that if you sum up the exterior or the external angles, it is clear that the sum is now going to be less than 2 pi, right. So if you compare this figure to the figure of the regular triangle that I drew earlier, it's clear that these external angles for this fat triangle will tend to be smaller than the external angle if the edge was a straight line, right. On the other hand, let's do the same exercise for the thin triangle. Right, so here you see that the external angles tend to be bigger, and so if you now sum up the external angles, the answer would likely be bigger than 2 pi, right. Okay, so let's try to understand whether there is some correction term one could add so that one would again get the answer as 2 pi. So for instance, can one add some positive correction term here so that the sum total is 2 pi, and similarly can one add a negative correction term here so that the sum is again 2 pi. So now if you notice in this picture, right, so look at the tangent vector at A1 to this curve joining A1 and A2, and look at the tangent vector at A2. So you see that the tangent vector has actually turned. On the other hand, if these were connected by a straight line, then of course there is no way that I mean the tangent vector doesn't turn, right, as you move along the curve. Similarly, let's do the same thing for for this. So again the tangent vector has curved. So I'll denote this by theta 1 2. So that's the amount the tangent vector curves as you or turns as you move from A1 to A2. Similarly, as you move from A2 to A3, the tangent vector again turns, and you do the same exercise here. Okay, so I'll denote this by theta 3 1. So in each case you notice that the tangent vector is always turning in an anti-clockwise direction. So whenever my tangent vector turns in an anti-clockwise direction, I call that change of angle, I keep the sign of the change of angle as positive. On the other hand, let's come to the picture of the thin triangle. So here at A1 you start off with this tangent vector, at A2 you have this tangent vector. So it has moved from this to this, right. So this is the tangent, the change of or the turning angle of the tangent vector, which I will call by theta 1 2 prime. Now you notice that for the thin triangle the tangent vector is actually turning in a clockwise direction. Okay, similarly one could do the same exercise for the other tangent vectors. So it turns from here to here. So again it turns clockwise, in a clockwise direction. I'll call this theta 2 3, and then at this point the tangent vector is this and it turns to this, right. So that's theta 3 1. So here theta I plus 1 prime, I want it to be negative because the tangent vector is turning in a clockwise direction, whereas here the turning angles, my convention is that I call them positive. Okay. So now if you do a little bit of bookkeeping, this is a simple exercise. If you do a little bit of bookkeeping, the following is not hard. That if you take the sum of all the external angles plus if you take the sum of all the turning angles, then that is actually going to be 2 pi. So if you take into account this sort of turning, the fact that your tangent vector to the curve actually turns, and if you do careful bookkeeping, actually calculate the angle that it turns and then add that back into your sum angle formula, then you actually get 2 pi, right. Similarly, so for the fat triangle you get this, and similarly for the thin triangle also you can do the bookkeeping, that summation I going from 1 to 3 epsilon I prime plus summation I of the turning angles, that is actually 2 pi. And the point is, our convention forces this to be a positive term and this to be a negative term. So this explains our earlier observation that for the fat triangle, if you add up the external angles, then the sum of angles is actually less than 2 pi. On the other hand, for a thin triangle, the sum of angles is actually bigger than 2 pi, right. Okay. So to summarize what we have now observed, for a curved triangle in R2, we basically have that sum of the external angles plus the total turning angle this is actually equal to 2 pi. Okay. So this is a fairly nice generalization of the sum angle property to very general curved triangles. You no longer need the sort of edge connecting the two vertices to be a straight line. So this is all well and good, except given a general curve, how do you actually calculate this? How do you calculate the turning angle? Okay, this is a question I am going to address in the next lecture. So the turning angle is actually going to be computed by calculating the total curvature of the plane curve. Okay, so the turning angle in some sense turns out to be the integral of the curvature of a plane curve. Okay, so I'll get to that in the next lecture. All right, so this is about curved triangles. I mean, let me now see if I can address my second question, which was namely what happens to the sum angle property on curved surfaces, right? Sorry. Oh, sorry, I wanted the blue color. So let us take the simplest curved surface that we are all familiar with. So let us talk about the sum angle property on the sphere. Okay, so I want to understand triangles on a sphere, but a natural question is what is really a triangle, right? So let us go back to our original definition of triangles. A triangle is basically a figure made up of three vertices. So maybe let me write this down. So recall a triangle is a figure with three vertices and three edges where the edges are shortest paths. I mean, there are straight lines in the plane, but what is really a straight line? A straight line is basically the shortest path joining any 2 points, right? So the edges are the shortest paths between the vertices. Okay. So the key point is the shortest path between the vertices. So this happens often in math, that you have a certain theorem that works well in a certain regime, and then if you would like to generalize it to a different situation, you need to have the right kind of definitions, right? So in this case, I mean, we need to really make sense of straight line paths on curved surfaces like the sphere, and the way to generalize the definition of a straight line is exactly this, that a straight line is precisely the shortest path between the vertices. Now let us look at the sphere. So now consider the sphere. So I am going to take the two-dimensional sphere of radius r sitting inside R3. So this is just the set of points x, y, z in R3 such that x squared plus y squared plus z squared is r squared. So it turns out that given 2 points P and Q, the shortest path from P to Q is a meridian or a longitude, or it is also called a great circle. Okay, so just to draw a picture, you have a sphere here. The sphere is very symmetric, so I can always assume that one of my points is actually the north pole, and let's say your other point is here. Then if I denote the south pole by P prime, there is a unique longitude going from P to P prime, which passes through Q, and of course then it goes around on the back side of the sphere. So in this case, the shortest path between P and Q is basically going to be this the small segment in this great circle, in this meridian, right. So if it's actually not very difficult to show from basic calculus that if you take any other sort of path connecting P and Q, that's actually going to be a longer path. So it's actually also of great practical use because for instance, if you want to fly from Mumbai to New York, you basically, the airplane essentially follows the path that is obtained by connecting these two by a meridian or a great circle. Of course, in actual life there are also headwinds, and the wind might change directions and so on. So but approximately the plane follows this sort of great circle path. Okay, so now that we understand, so a triangle on a sphere is a figure made of 3 vertices and 3 edges, such that the edges are the shortest paths. Okay. So now one can ask whether the sum angle property also holds for the sphere. So let me just give you an example. Let's consider the sphere. Let's say A1 is a point here, and this dotted line, let's suppose that's the equator. Let's take 2 points, 2 of the other vertices on the equator, such that, so now you join them by longitudes or meridians, such that the angle that they make with the equator is 90 degrees, and I mean the angle with the equator will always be 90 degrees because I mean that's basic geometry, but we choose the points A2, A3 so that this angle is also 90 degrees. Okay, so in this case, let's measure the sum of angles. So clearly the sum of angles of this triangle is 3 times pi by 2, which is obviously bigger than pi, right. So on the sphere we have now a triangle whose sum of angles is actually bigger than pi, and the discrepancy, so the discrepancy is precisely pi over 2, right. So it's pi over 2 above pi. Pi would be the correct answer in the plane. So on the sphere you now have a triangle which whose sum of angles is actually pi by 2 bigger than pi. Okay, so let me there's one sort of curious thing. If you look at this triangle, what is the area of this triangle? So note that the area of the triangle, well, how do you calculate that? The area of the full sphere is 4 pi times r squared, because r is the radius. So surface area of a sphere is 4 pi times r squared. The triangle that I have is basically 1/8 covers 1/8 of the surface area. Why? Because you can imagine that if you if you make these angles of pi, you can have 4 such triangles in the upper hemisphere and 4 in the bottom hemisphere. So that makes 8 triangles. So it's actually 1/8 of 4 pi r squared, which is pi by 2 times r squared. So the discrepancy, I'll call this delta. So this discrepancy delta is precisely 1 by r squared times the area of this triangle. Okay, so now what is this curious factor of 1 by r squared? Imagine you have a sphere of really large radius. Then essentially if you live on that sphere, so think of humans, us living on the earth, our ancestors thought that the earth is flat, right? Why is that? It's because the radius of the earth is much larger than the size of any human being, right? So if you take a sphere of really large radius, it actually appears almost not curved, right? On the other hand, if you take a really tiny sphere, let's say a table tennis ball, clearly you can see the curvature of that sphere, right? So that means that this 1 by r squared essentially measures how curved the sphere is. Okay, so this discrepancy is actually essentially the total curvature inside the triangle. Okay, so this turns out to not be a coincidence. I'll state a very general theorem, and I'll indicate how to prove that, and maybe the point of the next 2 lectures is going to be to make sense of whatever I've written here, that the sum of angles, the discrepancy with pi is essentially related to the total curvature contained inside a triangle. So of course we need to define what curvature means, and that's going to be the point of at least for these simple surfaces, that's going to be the point of the next 2 lectures. So let me state the general fact about spheres. So let A1, A2, A3 be a triangle on the sphere of radius r with interior angles alpha 1, alpha 2, alpha 3. Okay, so then the sum of alpha i's is going to be pi plus some positive number, and what is that positive number? That's precisely going to be 1 by r squared times the area of the triangle. Okay, so let me maybe in the next 5 minutes let me indicate how to prove this. So let me draw a picture. It's actually completely elementary geometry proof, so I thought it will be a nice thing to actually work this out together. So this is our sphere of radius r. Let me take a triangle. So in order to make the picture look better, I think I should carefully choose my great circles. Actually, let me use different colors. Okay, and for the third one, we choose blue. Okay, so this is going to be my triangle A1, A2, A3 with these angles alpha 1, alpha 2, alpha 3. Okay. So I want to calculate what the sum of angles of this triangle is. I do the following: I continue my my great circles on the other side of the sphere. Okay, so you notice that on the other side of the sphere there is another triangle formed, which I will label as A1 prime, A2 prime, A3 prime. So one way to think of this is, let's say your sphere is really a bulb, and your original triangle, you basically put some solid material there and shine a torch light, then essentially this other triangle is basically the shadow that's formed on the other side, right. So you have this sort of shadow triangle here. Okay, so now I want to do the following. I want to consider this sector. So I take alpha 1 and I consider this sector which goes to the back of the sphere. I call that S1, and I want to take the other sector formed by this angle alpha 1, and I want to call that S1 prime. Okay, so this sector is S1, the other sector is S1 prime, and I similarly do the same thing to the other angles. Now what will be the area of S1 plus the area of S1 prime? So you can imagine that if I open up alpha 1, so that alpha 1 is equal to pi, so if alpha 1 were pi, then these two sectors would combine to cover up the entire sphere, right. So then the area covered would be 4 pi r squared. Right now my angle is alpha 1, so then by the usual ratio thing that we learn in high school, the area is going to be 4 r squared times alpha 1. Right, so this area is going to be 4 r squared times alpha 1. Similarly, area of S2 plus area of S2 prime is going to be 4 r squared times alpha 2. Area of S3 plus area of S3 prime is going to be 4 r squared alpha 3. But now you notice that if you take all these sectors, they essentially cover up, I mean they basically cover up the entire sphere, right. On the other hand, these each of these triangles is counted once in each of the sectors, right. So if you add up the areas of these sectors, that's basically going to be the full area of the sphere. But this original triangle is counted thrice instead of being counted once, and the shadow triangle is also counted thrice instead of being counted once, and of course the shadow triangle and this triangle are congruent to each other. So that means you are actually counting 4 times the area of the triangle in excess, right. So you get this formula. On the other hand, what is this? This is precisely 4 r squared times the sum of angles. What is the area of the sphere? That's 4 pi r squared and plus 4 times the area A1, A2, A3. Now if you cancel out 4 and divide by r squared, you get precisely this formula. Okay. So this is an elementary proof of this very general sum angle formula for triangles on the sphere. Okay, so maybe this is a good time to stop the first lecture. In the next lecture I am going to talk about the curvature of plane curves in an attempt to extend to generalize this thing that we saw with the fat and the thin triangles. So that is the goal for the next lecture, and in the third lecture I will then try to extend the sum angle formula to curved triangles on curved surfaces. Okay, so that will be a generalization of this formula for the sphere that we proved. Okay, so that is the aim for the next 2 lectures. Alright, thanks for your attention, and I will see you in lecture 2. Thank you.